All right. And also, I know there's a couple people that are going to be out today, so hopefully I can give them this information. All right, so you read through closure. Hopefully the little cartoon helped. Basically, it's like you have a party, you have an invitation list, a guest list. It's a closed list. It's telling you that if you're not on the guest list, you're not allowed in. All right. If it's a store, the closed sign is up. You know, like if you've ever, I don't know how much experience you have with this, but if you've ever gone to like Target right when they're closing, you'll see some people milling around inside, but the door will be locked, you can't get in. It's just because they made the cut. They got in there before the store closed. So they can finish their business and leave even though the store is officially closed. They're just not letting any new people in. Right? So that's kind of like an analogous relationship. So something that we can think about in real life that connects to this, but it's not going to help us understand the numerical components. All right. So definition-wise, we're looking at a set being closed under an operation if and only if. By the way, just a side note, if and only if has an abbreviation of IFF. So when you're looking for typos, if you come across IFF in one of my packets, save your energy. It's not a typo. All right. So if and only if the operation, and these are the four basic operations. It could be any operation, but we're focusing on these. On two elements of the set produces another element of the set. Not close to the opposite of that. Right. So you can just read through that. Basically, what we're saying is if you perform an operation on any two elements in a set, let's say a set of even numbers. If I perform an operation on any two even numbers, will I get an even number only as an answer? Well, it depends. It depends on what the operation is, right? But that's the idea. What you're starting with and what you're ending up with belong to the same category. All right, that's what closure is really talking about. So when you're going through these examples, you're doing it with an eye on, I have a set and an operation. If I were to operate on this set, will I get only a value within that set? All right? So the number 1, is that closed under multiplication? Yeah. Just making sure my thickness is the way I like it. All right, so yes. And that's because, we'll just throw in an example here just to justify it. 1 times 1 equals 1. All right. All right, the number 1 is written in the set only once because there's only the one unique value in there. But we could use the number repeatedly. If we were talking about division, we'd say 1 divided by 1. Addition, 1 plus 1. So just a quick question. Is 1, the set of the number 1, closed under addition? No. Why? Yeah, if you add 1 and 1, you get 2. 2 is not in the given set. The given set only contains the number 1. If you subtract 1 and 1, you get 0. 0 is not in the given set. The given set only contains the number 1. All right. So how's about number 2? Under multiplication, is the set of 0 and 1 closed? We're saying yeah? All right. Now, the yeses can get out of hand pretty quickly if you start listing examples. Because if I were to actually list all the different ways in which this set is closed, it starts getting longer and longer the more elements I add to the set. So we can just say yes. I just did the example for the first one because it was really easy. What you're going to want to do when you have a no is make sure you show an example of why it doesn't work. That's called a counterexample. All right. So here, if you just have it in your mind, all the different ways that it play out, like 0 times 1 is 0, that's in the set. 1 times 1 is 1, that's in the set. 0 times 0 is 0, which is in the set. you've checked all possibilities, you're looking at something that is closed. All right. Zero, 2, and 4 under subtraction. What do we got there?
Closed.
We get a closed. So I could subtract any two pairings of values in any order and get only numbers in the set. So there's a reason why I haven't written closed or yes down.
Oh, wait, can you like negative?
Yeah, it could be negative, yeah. So we're going to say no. The counterexample is that 0 minus 2 is equal to negative 2. All right, you can play around with the orders, and you can play around with the pairings. So if I did 4 minus 2, I'd be fine. 4 minus 0, I'd be fine. 2 minus 0, I'm fine. But if I start going in the other order, 0 minus 2, not in the set. 0 minus 4, not in the set. 2 minus 4, not in the set. All right, but all you have to do is show one instance in which it's not closed, and you're good to go. How's the boot number 4 there? We say yes, no, what? Yeah, we're going to say no on that one. And our counterexample is what?
4 plus 8 is 12.
Well, we're looking at division here. 4 divided by 8 is equal to 1/2. Not in the set. Decimal value 0.5 if you want. All right. Starts getting a little funkier when you have the ... That's showing that trend continues infinitely. All right, so forever and ever. So what do we say about number 5? Add any two of these values. Will I get, because basically this is saying the set of even numbers, right? Starting with 2 and going on. If I add any two even numbers, will I get a number that's even?
Yeah.
Yeah. One, 3, 5, so that's looking like odd numbers. So ask yourself, you want to start thinking generally here. Can I multiply any two odd numbers and get a result that is odd? Seems right, right? Well, definitely 1 times anything is going to work. If you did 3, you just start playing around with numbers. 3 times 7, 21, that's odd. 5 times 5 if you want. You know, start squaring values. They're all in the set, right? 5 times 5 is 25. 3 times, you want to get crazy, like 3 times 33, 99. So we're looking at a yes here. All right. This makes sense?
Yeah.
For the most part, yeah. I mean, you can see how there are certain situations where the problem is going to be more challenging than other situations. But conceptually, it should be, it's just a matter of testing the quality of the numbers. You say, this is what I have, this is what I have to do with what I have, and once you get the result, you want to see how it relates to what you had initially. All right. And also, you know, following directions is always important. Most common cause for mistake on this, you know, assuming a student goes into a test knowing what closure is, the most common cause of mistake is forgetting to justify the answer when the question asks you to do it. It says give a counterexample and you just say no without telling me why. Right? So as long as you do that, as long as you show me why, you're going to be in good shape. You know, and have that in mind for just about everything. You know, always think to yourself, have I justified my answer? Because if you haven't, then you know, odds are there's more work that you need to show. All right. So, example, we're good there. The practice solved example, you can see that. So that's pretty straightforward stuff, I think now. So let's flip on over to the next page. Okay, so this question, does this mean that even numbers are closed for all operations? All right, because we tackled that. We said even numbers are closed under addition. Are they closed under division? Are they closed under multiplication, and so on? All right. If you divide two even numbers, is the quotient always even? We have an example of that not being the case. If you divide any two even numbers, your result could be fractional, which is not an even number. Right. So then, in that case, we would say the set of even numbers is not closed under addition. I like these questions a little bit better because, you know, it's a little bit out there, I guess. You have to do a little bit more thinking. It really tests your knowledge of the concept of closure. You're not really just kind of steered into a particular answer. So you're given a set, and you have to determine which operation it would be closed under, right? So now, it just bear in mind that, you know, these are multiple choice questions in a lesson sheet. So it could be possible that maybe we have more than one right answer. On a test, just so you know, because I'm not a terrible person. That's true statement. I don't do multiple choice questions where there's more than one right answer on a test. All right, and I'm not big on choice one is this, choice two is that. They're both right because choice E says A and B are correct. You know, it's not a mind game. It's the correct answer is in there. You just have to find it. All right. So I try to be at least a little bit nice when it comes to that. All right. So this set, would we say it's closed under addition? Negatory. Why is that? Give me the counterexample. Indeed it is. That's a hard conversation to have when you get home. You go home and say, parents ask you, how was math class today? You say, oh, it was really hard. I didn't really understand anything. And they say, okay, let me see your notes. We'll figure it out together. And then they see this. 1 + 1 = 2. And they're like, wait a minute, I thought you said it was hard. You gotta be kidding me. Yeah, so, yeah. 1 + 1 = 2. Another one? -1 plus -1 gives us -2. So that's another possibility. All right. Is it closed under subtraction? What's my counterexample there? Yeah, -1 minus 1 equals -2. It's actually, it's kind of interesting where we end up with a counterexample that we could have used for addition, because we could think of this as -1 plus -1, which is a counterexample for addition, or -1 minus a +1. All right, so where the second negative sign is the operation. So we're looking at something like this, with this guy being the operation. Now it looks like an absolute value symbol. I just made it look awful. Multiplication. Yep-er-do. I don't know how to spell yep-er-do. Is it an I-R or E-R? I'm not really sure. Yeah. Any possible pairing. -1 times -1 is 1 in the set. 0 times 0, 1 times 1. -1 times 1, 1 times -1. Either of these values times 0. It's all good. All right. Division. Running through the possibilities in your head, right? What do we say there? No. Give me the counter. There's actually two possibilities that you can say. What's any number divided by 0? Negatory. Undefined. I don't know why I opted to go script here. I don't know how to write in script. No, I do. At the Catholic school for a year. Kind of force it on you, but I never got the hang of it. Yeah, anything divided by 0 is undefined. So if you type it in your calculator, type in a number divided by 0, it's going to give you an error message. It's going to say, I believe, error undefined. Or maybe error non-real. But it doesn't give you an answer. That's the whole point of this. All right? You can divide 0 by any number. 0 divided by any number is going to give you a 0. But any fraction in which 0 is on the bottom is undefined. So that also includes 0 over 0. 0 over 0 is not equal to 0. It's not equal to 1. It's some indeterminate value. So it's some value that we can't find some number we can't find the value of. Right? All right, so now we start jazzing it up a little bit. You can expect a problem like this, definitely on a quiz or a test, definitely on the Regents exam, it always comes up. Which set is closed under division? This becomes challenging because if you don't know what these sets are, then game over, right? You might know what closure is, but now it becomes a guessing game because I don't know what whole numbers are, for example. It's all over at that point, all right? So, if you don't know what they are, then you go right on back to page 1 in your packet and take a look at that diagram right in the middle of the page. Right below that is the table that has some examples. At that point, you should be in pretty good shape. All right, so what do we say for A, for the set of natural numbers? We say that's closed or not closed? Can I, yeah, it's not closed, and what's my example? One divided by 2. Yeah, anything that gives you something other than a natural number. So the natural numbers, also known as counting numbers, start with 1 and increase by whole number values from then on out. So 1, 2, 3, 4, 5. So if you can count it, it's a natural number. All right, whole numbers are the set of natural numbers, but they also include the number 0. So our conclusion for natural numbers should be exactly the same as it is for whole numbers, because that counterexample still works. What about rational numbers? What are we saying there? We say yes or no? Yeah. All right, rational numbers, the root word of rational is ratio. Ratio is another name for fraction. So that's telling us that we can have fractions in our set. So I know that based on what we determined here for natural and whole numbers, that when you divide any of those kind of numbers, you could get fractions as a result. So this set is allowing for fractions, right? Which is good because that's the only thing that was missing. And so therefore none of the above does not apply. All right. So we have a few different sets here. This is the last problem we're going to do together. Then you can have some time to do some stuff on your own. How many of the following sets are closed under the given operation? So we have, this looks like even whole numbers. This looks like just whole numbers in general. And this looks like, well, it looks like what it is. These are those specific values. All right. So, is this set closed under addition? Yes or no? Yes. I'm going to put a little check mark there. I'm going to go green. Yeah, add any two even numbers, you get an even number. So we know that because of what I just said, and also because we've done this problem already. All right. If I add any two, oh, sorry, subtract any two whole numbers, will I get a whole number?
No.
No. Give me an example. 0 minus anything, right? Because you're going to get a negative. All right, so big red X on that one. And if I multiply any two values in that last set, what am I looking at? Yes or no? 2 times 2, right? Yeah, no bueno. So exactly 1. And boom goes the dynamite.